Welcome back. We're learning how to use spreadsheets to analyze physics data, and in parts 4 and 5 we're really getting to the heart of why spreadsheets are so valuable as tools for analyzing data.
So the next thing I'd like to do is show you some basic calculations that we can do using Excel, just using simple algebra. So what I'd like to start with is to do a calculation right here for our time interval between each frame. So what we need to do to calculate the value of the time between each tick is we need to take how many frames we had divided by the number of frames per second. So I would recommend before you start working out calculations in your spreadsheet, do them by hand on a separate piece of paper so you know what the math is for a sample calculation, and then you can use the calculation or the formula you come up with in your spreadsheet. So what we need to do is calculate the time between each dot, which is also called, we call it delta t, but in reality, since it's a cyclic process, we could also use a capital T, which represents the period. And we can also calculate the frequency if we wanted to use that. And the frequency is related to the period, as you'll see. So we found that one dot is made every 4 video frames, so there's 4 frames per dot. And our slow-mo video was recorded at 240 frames per second. So how can I use 4 frames per dot and 240 frames per second to come up with the time per dot? Well, if we use dimensional analysis, we can actually look at our units canceling here. So our time should just equal the number of frames per dot divided by the number of frames per second. Our frames cancel top and bottom, and the seconds in this complex fraction get flipped up to the top. And 4 divided by 240 is 1/60th second per dot. This cyclical time that we're seeing, the delta t, in a periodic function is also known as the period, t, capital T we use for that in seconds. The frequency is actually the number of dots per second instead of seconds per dot. Well, that's easy enough. That's just the reciprocal. So to calculate the frequency from the period, we just take the reciprocal, f equals 1 over t. And it looks like we have 60 hertz. So 60 hertz, that's an important number because it turns out that 60 hertz is the frequency of the power coming out of those wall sockets in your house. And that's what our little ticker tape timer is plugged into. So that wall power that you're providing, 120 volts, 60 hertz, is actually driving our ticker tape at 60 hertz. And so it's making one dot every 1/60th of a second. So we're actually using the frequency of the electricity coming out of your wall socket to actually drive our little ticker tape timer. So let's repeat that calculation right in our spreadsheet. So we know that to get our period, t, and I'll add period to this, what we can do is we're going to take our number of frames per dot and divide it by the frames per second of the film. So to create an equation in Excel, I type in an equal sign to tell the cell that this is an equation, and then I'm going to divide the 4 frames divided by the 240 frames per second. So all I have to do is to actually point to the things I would like to divide. So I'm going to point to this and click. There's my 4, and you'll notice what it did. Instead of putting a 4 here, it actually put F6, and that's actually our cell reference. It's actually taking column F, row 6, and it's going to plug it in right below here. So that's called a cell reference. And I'm going to divide. I'll hit the divide key now. There's a slash. And I want to divide by the 240. So I'm going to go up to the 240, and I'm going to click on that, and it automatically enters that for me. So here I am in column F, row 5. So it's going to take column F, row 6, which is the 4, divided by column F, row 5, which is the... And there's my period, which is 1/60th of a second, or 0.016667, and this goes on forever. In fact, if you wanted to see more decimal places, I could shift it over with my decimal tool to get as many as I wanted, or if I don't need that many, I can shift it back. So maybe we'll go with 3 significant digits on that. So there's our time per dot. Now let me just show you one more nice thing about this methodology that they use. If I double click back into this cell, there's my formula again. You'll notice the formula also shows up above here in my formula bar. That's why it's called a formula bar. And you'll notice that these are color coded. The F6 is colored blue, so I can actually see where it came from. You see this cell has a blue box highlighting it. and my F5 is highlighted in green. And so I can easily see on my spreadsheet once I click into the cell where my numbers are coming from to fill in this formula. So how do I calculate the frequency? I double click into my cell once again, and I'm going to use a formula that we worked out on our PowerPoint slide. It equals 1 over our period, and our period is right up above here, so I'm going to go up to the cell and click on it, and it automatically enters that for me. And then I'll hit my enter key, and there's my frequency. It is 60. That's what we said below, 60 hertz. I'm going to save before I go any further. So there's examples of how to do calculations in cells. So we've seen how to use the autofill feature. We've seen how to do formulas in cells. Now let's put those two features together to show you the real value of Excel, or any spreadsheet. So what I'd like to do is take these calculated values that I just came up with up here and use them to calculate my times in this row. Well, my first time should be what? Well, I'm going to put that up in my initial conditions. My time 0. And I'm going to set it equal to 0. And that's going to be in seconds. You'll notice Excel is smart. It noticed I was doing the same type of formatting, and so it automatically pulled down this green cell for me. All right, so what I'm going to do here is I'm going to use an equation to fill all of our time values. Well, the first time value, I'm simply going to use my initial time. So I'm going to use an equation once again, double click, I'm going to set this equal to that initial time right there in cell B8. All right, so it automatically, I pointed and clicked to enter the B8. So I have an equals B8. Hit enter. All right, there's our first time. So for each subsequent time, all we need to do is add our delta t. So I'm going to click into the next cell. So I'm going to equals, I've got to take the previous value, which is at 0, and I'm going to add, hit the plus sign, I'm going to add my delta t, 0.167. And you'll notice my next time should be the sum of which cells. Let me just double click on this so you can see where the colors are showing up here. 0 is the B for 13 in blue, and in green it's cell F7, which is my delta t. So obviously 0 plus 0.0167 is going to be 0.0167. I'm going to hit enter. Now, how do you think I should fill in all the rest of these cells? Well, what you're probably going to want to do is use the autofill tool. And let me just show you what happens when I do that. If I click on this autofill tool and I click and drag it, you'll notice there are no numbers showing up alongside of this showing what's going to come in there. But let me just show you what happens. It gives me, it tried to copy something, so it copied a 60.0167 for some reason, blank, 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 and then a value. Let's just click into these to see what's happening. Here's my original formula, and I'm going to use the arrow key to key down here. So I've got B13 plus F7. My autofill made the next one into the following. It changed it to B14 plus F8. The next one turned into B15 plus F9. And you'll notice what's happening here. Each time this cell moves, these blue and red cells are moving down with it. Well, we wanted this first cell to be the cell right above it, and so that one's correct, but we don't want this green cell to be moving down. So the autofill is helping us in one sense. We do want to, from one cell to the next, we want to always point to the previous cell to get the old time, and we want to add the same time over and over again. But what's happening is it's picking up our previous time. That's good. But what it's doing at the same time, it's moving, instead of staying on this cell and being stuck to it, it's moving that down. And if I move down one more cell, you can see it move down one more here. If I move down one more cell, I move down one more here. So we want the blue numbers to move down, these ones here, but we don't want this number to move down. We want it to be locked in on this number. So what this is called is we want our first number to be the old time, and as we move our autofill tool, we want this always to be relative to the cell above it. So it's called a relative frame reference. So as I move it down one, we want the blue one to move down one with it. All right, so we always want this to be relative to this black box. We want it to be one spot up from it. The green box, however, we didn't want to move. We wanted to have it fixed. We wanted to have a specific cell frame of reference. And that's called an absolute cell reference. You don't want it to move absolutely. So absolutely keep that right in the same spot. So here's what we're going to do. We're going to go back up to my original formula. So we want our cell B13 to change into B14, B15, B16 as we slide this down, but we want to lock in our B7, our F7. And all we need to do is insert a $sign in between each of the numbers on our cell reference that we would like to lock in place. So I could actually do that manually, just type in $1 and $1. But what I can do, if you hit the F4 key when I'm on the F7, and this is my function key F4, you'll notice that it automatically puts the $2 signs in for me. And that locks it in to this cell, and it will not move when I use the autofill key. It'll keep that locked in on this cell right here. You'll notice if I hit the F4 key again, it'll actually shift the positions of these $, these absolute references. $, gives us an absolute reference and doesn't let it move. So if I hit the F4 key again, it gives me $7. If I hit it again, it gives me $F7. If I hit it again, it goes back to the original value. So it cycles between the 4 different patterns you could actually use. And in this case, I want to lock in both the column and the row on this number. This is a constant that I'm using, and I'm going to keep it there. So I'll hit enter. And now let me grab this equation again, which is B13 plus $F7, and I'm going to drag that downward. And you watch what happens. There are all my times. And let me just click into some of these cells so you can see what happened. So we wanted B13 to be the cell right above to add to the old time, but we wanted to lock in on this cell over here. And go into the next one, and you can see it changed to the B14, but it kept our F7. Changed into B15, kept our F7. Changed into B16, kept our F7. So that automatically allows us to use values in the spreadsheet that we'd like to move along with it to calculate our values, but keep some things constant. And we'll do this again for these other calculations. We're going to do these other rows and columns. So let's try a few other calculations here. For example, we wanted to change our centimeters into meters into this column. So what I'm going to do is I'm just going to say equals, and I want to take whatever value here in centimeters and divide by 100 to go into meters. All right. Now I'll hit enter. Now you'll notice when I pull this down using the autofill tool, what do I want to happen? Do I want the C13 to change to a C14 and do the next number? Yes, I do. So I will keep that as a relative frame reference and let that float as I slide this down using the autofill tool. So let me hit enter, and then I'm going to take my formula here and I'm going to copy it down into the other rows. And as I do this using the autofill tool, it automatically calculates C14 next, C15. So the autofill tool automatically shifted this down, kept the divide 100 in each case, but then it actually went from C15 to C16 to C17 to C18. The problem we have with our data is that it appears that the ball is moving up the y-axis instead of down the y-axis. And so in other words, it looks as if we set up our y-axis to be positive as downward. I'd like to do it in a more traditional format. I'd like to have y to face upward, and so we should be starting at some initial height and dropping down from there. Well, our initial height is right over here, and so I'm going to put an equal sign. I'm going to put starting our initial height, and what I'll do is I will subtract the amount we've dropped. So you can consider this number here the amount we've dropped so far. So I'll take 1 meter minus, this is the amount we've dropped at time 0, and that will be the formula used to calculate this column. Now, as I drag this down, I do not want the 1 meter to change. I want to take 1 meter minus however much distance I've traveled so far. So the B5 I want to lock in place with a fixed cell reference. So I'll hit my F4, click on that, and hit F4 to put my dollar signs in. But my distance that I've traveled so far, I would like to change. I'd like to subtract D14 next and D15 next and so on and so forth. So that will be my formula for that. And then let me just run down a couple of these just to show you that it's working. How can I calculate a velocity based on my original values here? Well, I'm going to, first of all, I'm going to set my first velocity to 0. So my other experimental velocities, I didn't actually measure velocity directly. So for all my future points, what I can do is take the slope of the secant between our two position values and our time values and use that slope as our average velocity between those 2 points. And of course, this is done over a 1/60th of a second time interval, so this should be a fairly good approximation of what the real velocity is. Even though we're not directly measuring velocity, we can come up with this as an approximation. So let's do that. So we're going to use our average velocity equals delta y over delta t. So I need to take my final y position. Here's my final y position, and here's my original y position. So I'm going to take final minus initial, and I'm going to divide by our change in time. So I could go down here and say time final minus time initial, but since this delta t is always the same and I have it calculated up above here, I'll just use that instead. So I just clicked onto it to pull it in, and because we don't want the delta t to start changing its numbers as I use the autofill tool, I don't want to go from F8 to F9 because that'll move it down and pick up some weird data here. I'm going to hit the F4 key to lock it in place and hit enter. So it looks like our initial velocity started at 0 and then it went to negative 0.24 meters per second, and let's see if it increases if I pull this down. Sure enough, it's increasing our velocity. And we'll fill out these other ones in a moment, and I'll show you why I'm doing that. For our experimental acceleration, we can do the same type of calculation. I'm not sure what our original acceleration is. I'm going to leave that alone. But what I'll do is I'll take the next 2 points, and I'll take point 1 and 2 for our first acceleration calculation, and I'll use our delta v over delta t formula to calculate an average of the slope of this secant. So I'm going to take my final velocity minus my initial velocity and divide it by my time, change in time, and once again I'll just use this as my change in time and hit my F4 to lock that in as an absolute reference, hit enter. So it looks like my acceleration is negative 14.4 meters per second using this calculation. When I go down to the second calculation, it's dropped down to negative 7.2. Now, every time I do this, it's essentially a form of a derivative, and I'm going to get further and further away from my values, and I'll pick up any little errors I have in my measuring here and any other errors in the system, and they'll get amplified every time I go through this process of taking a derivative. I took a derivative here, and hopefully those are reasonably good values. I took a derivative again, and these values will get a bit flakier and flakier. But they should be around 9.8 meters per second, and they're not crazy off, and so that's not too bad. Now, theoretically, what should my y, vy, and ay be? Well, we know from motion equations 5, 6, and 7 what these should be. And I'm going to put for our initial values, this is our initial position is 1. Our initial velocity is 0. Oops, sorry, I put an equal sign here. 0. And our initial acceleration should equal negative 9.8. In fact, our initial acceleration is that forever. That is a constant, so I'm going to change this to lock in on that cell. And there's my acceleration, negative 9.8. Now, to calculate the rest of these values, I'll just use my motion equations. So my position should equal 1/2, which I'm going to put at 0.5, times, and I'll use a star for times, my acceleration, which is right here, my theoretical acceleration. I'm going to lock that in because I don't want that to move when I pull my formula out, times my time squared. My time, I'm going to use my time reference right over here. The time at this spot is 0.0167, and I need to square that. I can use a caret for a square, plus I need my velocity, my initial velocity times time. And my initial velocity is 0, so this term will drop out. But just to show you that I can put it in, and later on if I did have a different number I changed up here, it would ripple through for me. So here's my initial velocity times my time again right here. Now, the B6, my initial velocity, I want to lock that in, so I'm going to go back and hit F4 on that. My time, however, when I drag this formula down, I want my time to follow along my column here, so I'll keep that unlocked as a relative cell reference. Plus I have to add in my initial position, which is right here. And that once again has to be locked in place. That's the same for each one of these formulas. Hit enter, and there's that value. Let me just pull it down one more time, and you can see that's my next expected value. So for velocity, what I'll do is I'll use the same type of formula. I'll use equation number 6. And so my velocity should equal my acceleration times time plus my initial velocity. So my acceleration is right here. I'm going to lock that in. Plus, times my time, which is over here in the time column. That I want to float. As I roll this down, this number should move with me. Plus my initial velocity, which is right here. And I'm going to hit that and lock that cell in. So I'm locking into my 2 initial condition cells, and I'm letting my time roll with my autofill. And there's that equation. And my acceleration is the same acceleration the whole time. And so I can just, since this is already locked in up above, you can see, remember your formula shows up here as well. That is a good formula already, so I can just pull that down. All right. So these formulas that I just entered for my experimental y, which is a direct measurement, and then my experimental velocity and acceleration, which are based on calculations, basically a form of derivative, and then my theoretical, are all lined up here and ready to go and fill out the rest of these. Now let me show you how we can do this in one shot here. I can grab all these at once, drag them all down using my autofill tool, and there's my whole table of values. Voila.